Hello and welcome to Data Engineering with Subhadip. In today's video, we are going to decode Python's concurrency models. We will explore the differences between multiprocessing and multithreading, specifically for data engineering tasks. Here is what we will cover today. We will start with the basics of concurrency, then discuss the infamous Global Interpreter Lock, or GIL. After that, we will dive into multithreading and multiprocessing, understand when to use them, and finally, we will run a performance benchmark to see them in action. First, let's clarify two key concepts: concurrency and parallelism. Concurrency is about managing multiple tasks at once, like a chef juggling different steps of a recipe. Parallelism is about running multiple tasks at the exact same time, which requires multiple chefs, or in our case, multiple CPU cores. Now, let's talk about a crucial concept in Python concurrency: the Global Interpreter Lock, or GIL. The GIL is a lock that ensures only one thread executes Python bytecode at any given moment in a single process. This is the main reason why Python multithreading doesn't speed up tasks that are heavy on CPU calculations. Multithreading involves running multiple threads within the same process. Because of the GIL, threads are most effective for I/O-bound tasks. When a thread is waiting for an external operation, like a network response or a file to be read, the GIL is released, allowing other threads to run. This is great for tasks like web scraping or querying multiple APIs concurrently. Multiprocessing, on the other hand, creates completely separate processes. Each process gets its own Python interpreter and memory space, which means it is not limited by the GIL. This is the perfect solution for CPU-bound tasks, like complex mathematical calculations, data aggregations, or transformations on large datasets, as it allows for true parallelism across multiple CPU cores. It is also worth mentioning AsyncIO. This is a single-threaded, single-process model that uses an event loop to handle a massive number of I/O-bound tasks efficiently. It excels in applications that need to manage thousands of simultaneous connections, like a web server or a chat application, but can have a steeper learning curve. So, how do you choose? It is simple. Use multithreading for I/O-bound tasks. Use multiprocessing for CPU-bound tasks to leverage multiple cores. And consider AsyncIO for highly concurrent I/O-bound tasks, where you need to manage thousands of connections with minimal overhead. Now for the fun part, a performance benchmark. We'll simulate a common data engineering task, processing 10 large CSV files. Each file contains 1 million rows. The job is to read each file and calculate the mean of a specific column. This task involves both I/O for reading files and CPU for the calculation. First, here is our baseline code. It's a simple sequential approach using a list comprehension to process each file one after another. We will measure the total time it takes to complete all 10 files. Next, we implement the multi-threaded version. We use the thread pool executor, a high-level and easy-to-use interface for managing a pool of threads. We map our file processing function to the list of files, allowing up to 10 threads to run concurrently. Finally, the multiprocessing version. The code looks very similar, but this time we use a process pool executor. This will distribute the work across multiple CPU cores, each running in its own process, completely bypassing the GIL. We are using 4 workers, assuming a 4-core machine. Let's look at the results. As you can see, sequential processing was the slowest. Multithreading provided a modest improvement because it could overlap the I/O operations of reading the files. However, multiprocessing was the clear winner, with a dramatic speedup. This is because it could truly run the CPU-intensive calculations and file reading in parallel on different cores. So what are the key takeaways from this? First, always choose the right tool for the job. Understand if your task is I/O-bound or CPU-bound. Remember that the GIL is the main bottleneck for CPU-heavy tasks and threads. For most data processing jobs that involve both reading data and transforming it, multiprocessing will give you the most significant performance boost. And finally, modern libraries make implementing these patterns easier than ever. That's all for this video. I hope this gave you a clear understanding of when to use multiprocessing versus multithreading in your Python data engineering projects. If you found this tutorial helpful, please hit the like button, share it with your colleagues, and subscribe to the channel for more content. Thank you for watching.